All right, so in this video, one of one for the Walker circulation, we're going to talk about the Walker circulation in terms of its overview, its basic characteristics, modes of variability within that Walker circulation, especially as it relates to the El Niño Southern Oscillation, and the overall structure of the Walker circulation, focusing on the lower troposphere. So we have two mean tropical overturning circulations. Last week we considered the Hadley cell, which is the meridional tropical overturning circulation. And here we see it depicted in more or less its climatological mean, with ascent here centered on the equator and flow away from the equator at upper levels and toward the equator at low levels, with descent in the subtropics. The Walker circulation, on the other hand, is the zonal tropical overturning circulation, centered more or less along the equator, with ascent where it is relatively warm and descent where it is relatively cool. The lower troposphere is characterized by easterly trade winds. The upper troposphere is characterized by westerly flow. So this is a thermally direct circulation, just as the Hadley cell was. Ascent is maximized where it is relatively warm, and that happens to be typically in the western equatorial ocean basins, the Atlantic, the Pacific, and the Indian Ocean. Descent is maximized where it is relatively cold, and this tends to be in the eastern equatorial ocean basins, again, the Atlantic, Pacific, and the Indian Oceans. And why that is the case, we'll discuss here in the next few slides. This pattern of vertical motion, ascent in the western ocean basins and descent in the eastern ocean basins, governs where precipitation preferentially occurs. So if we think back to our tropical climatology lecture notes and slides, we saw that rainfall is maximized, especially in the western portions of the equatorial ocean basins, with somewhat less, especially away from the equator, in the eastern portions of the equatorial ocean basins. So the Walker circulation formally refers to that circulation over the Pacific Ocean, with the easterly trade winds from South America toward the maritime continent, Asia, and Australia, with ascent maximized near the maritime continent, westerly flow aloft, and descent off of the coast of South America. However, it's also come over the years to refer to the same type of circulation in the Indian Ocean, which is centered typically in the far western portion of the basin near to Africa, and the Atlantic Ocean, where you have maximum ascending motion as you reach towards South America. So over all of these equatorial oceans, the Walker circulation is characterized by easterly low-level winds, as we see here in the Pacific, the Indian, far western, and the Atlantic Ocean, and westerly upper tropospheric winds, again as we see here in the Pacific, the Indian, and the Atlantic Oceans. It's a little bit more complex in the Indian Ocean given its relatively small size and comparative dominance of the Pacific Ocean Walker branch of the Walker circulation. And as noted, although specifically referring to the Pacific Ocean's zonal overturning circulation, the Walker circulation terminology has come to refer to all of our zonal tropical overturning circulations, those in the Atlantic, Pacific, and Indian Oceans. So the Walker circulation is primarily driven by three forms of atmospheric and oceanic warming. I'm using the term warming here rather than the more generic heating because it is local warming, diabatic warming, that gives rise to the Walker circulation's ascending branch. And this is preferentially found again on the western edge of the equatorial oceans. The first mode is surface sensible heating of the equatorial land masses that are present there in the western portions of the oceans. Indonesia, or the maritime continent more generally, in the Pacific Ocean, Africa in the Indian Ocean, and South America in the Atlantic Ocean. We also have atmospheric latent warming, latent heating more generally, associated with thunderstorms. So these thunderstorms form in those landmass regions preferentially because that is where it is relatively warm. So you get relative warmth in a very moist, moisture-rich environment with low-level easterly trade winds converging from the ocean toward the land, and that's a rich environment to promote thunderstorm development. This has also helped in Africa and South America, so for the Indian and Atlantic Ocean branches of the Walker circulation, with easterly upslope flow. There are relatively high mountain ranges in eastern Africa and then in western South America associated with the Andes Mountains. And so the easterly flow hitting up against these mountains causes air to ascend, and more readily promote thunderstorm development in those locations, in addition to the surface sensible heat driving that process as well. And the third one, and perhaps the most important, but also the most novel in terms of what you've likely been exposed to earlier in your studies, is surface sensible heating associated with relatively warm waters in the western equatorial oceans. So we've kind of hinted that the equatorial oceans are warmer in the western portion of the basin and cooler in the eastern portion of the basin, but we haven't really said why. And when we talked about the Hadley cell, we really considered it to be uniformly warm, apart from land and water temperature contrasts at the equator. So we're going to want to dig in a little bit more as to why the waters might be typically warmer in the western equatorial oceans and cooler in the eastern equatorial oceans. We have a hint here that it's driven in part by easterly trade winds, but how? So let's take a look at how the ocean temperature typically varies with increasing depth along the equator. And this is depicted here for the Pacific Ocean. So we have the coastline of Asia here to the west, the international dateline here in the left center, and then the coast of South America here at the far right. We have temperature shaded in the colors here. It's listed as potential temperature, but this is nearly equivalent to temperature over the relatively limited depths that we're looking at here, from the top of the ocean to about 350 meters, roughly 1,000 feet, a little bit more deep in the ocean. In general, these ocean temperatures decrease with increasing depth below the surface, but they don't do so uniformly across the ocean basin. The depths over which this decrease is most rapid, so where you have these contours most tightly packed in the vertical and where the colors change most rapidly within the vertical, is known as the thermocline. And here we see that it is found at deeper depths, roughly 200 meters deep, here in the western portion of the Pacific Ocean, and at much shallower depths here in the eastern portion of the equatorial Pacific Ocean. So as we see through this figure, and as we've discussed already on this slide, the thermocline's not at the same depth everywhere along the equator. It's typically deeper in the western portion of the basin and shallower in the eastern portion of the basin. But why? So let's consider oceanic transport, and there are going to be two things that we take a look at here in this context. So this first one, the more basic one, we assume that we have land masses on the east and west sides of the ocean. This is taken to be approximately the Pacific Ocean. So you'd have Asia and the maritime continent here to the west, and you'd have South America here to the east. Increasing depth going down, water surface here with the squiggly blue line. So I've depicted the thermocline here, which we can approximate by the depth of the 20 degrees Celsius isotherm here. So it's deeper in the western portion of the basin and shallower in the eastern portion of the basin. And we have our easterly trade winds depicted here right at the surface of the ocean. So these easterly trade winds are constantly trying to push this surface water from east to west. So it's trying to take what's there at the top and push it away from South America and push it towards Asia and the maritime continent. So with land to the east, if you push away the water at the top, there's got to be something coming in to replace it. And that is generally coming in from below, what we call upwelling. So we've depicted this with this black arrow here, depicting the relatively cool, deeper subsurface ocean water being upwelled or brought upward toward the surface here. So that's associated with relatively cool ocean temperatures at the surface here in the eastern equatorial Pacific and eastern equatorial oceans, but also a relatively shallow depth to the thermocline as you push that upward, kind of advecting it upward by this upward directed vertical velocity. And conversely, on the western side of the basin, you're bringing that relatively warm surface water toward the west, where it then impinges upon Asia and the maritime continent, and that forces it to sink, or what we call downwell. And so that doesn't necessarily warm the upper ocean temperatures, but it leads to a greater depth of warmth over here in the western portion of the ocean basin. But there's a second and perhaps more important yet more complicated factor that influences ocean temperatures along the equator. Not just the difference between the eastern and the western portions of the basin, but all along the equator. And this is known as Oceanic Transport. So I have a complicated diagram here at left, but we're going to step through this in pieces to help make sense of it. So before we mentioned that we had surface wind that's trying to tug the surface water in the same direction as itself, although this is slowed down by friction associated with the water. So if I depict here the surface wind, this would be an easterly surface wind. There's a frictional force that acts directly opposite of that, so directed back toward the east. And if I take those two vectors and find the sum of those, I get this net tugging force given by the red arrow. So this is directed from east to west, but it's not as strong as the surface wind. However, this tugging force induces a Coriolis deflection. So this Coriolis deflection is 90 degrees to the right of that in the northern hemisphere and 90 degrees to the left of that in the southern hemisphere. So let's look at this in a force balance perspective as well. This red arrow here depicts our tugging force once again, and the Coriolis deflection associated with this is 90 degrees to the right of that in the northern hemisphere, given by the solid purple line, and 90 degrees to the left of that in the southern hemisphere, given by the dashed purple line, where these lines are the same length because the Coriolis deflection is directly proportional to that tugging force or that tugging velocity. So if I take the sum of those vectors, the tugging force and the Coriolis deflection here in the northern hemisphere, I get a net ocean current that is 45 degrees to the right of that surface wind here in the northern hemisphere. And in the southern hemisphere, I get one that is 45 degrees to the left of the surface wind here in the southern hemisphere. So then this process repeats as we keep going down within the ocean. That surface current, which is 45 degrees to the right or to the left of the surface wind, then tries to tug the water just below it in the same direction. And this too is slowed down by friction, and then this too induces a Coriolis deflection. So if we take a look at this near surface current here, this black arrow is just like what we saw with the teal arrow on the previous slide for the northern hemisphere. There's a frictional drag that acts directly opposite of that, and the summation of those two give me this red arrow here for this net tugging force, where I've only depicted the northern hemisphere component here for simplicity. So this Coriolis deflection, again in the northern hemisphere, is 90 degrees to the right of the tugging force. So let's take a look at how this impacts the ocean current a little bit below the surface. So I've depicted this tugging force from here at left with this red arrow here at right. The Coriolis deflection in the northern hemisphere is 90 degrees to the right of that. And so the summation of these two vectors, these two forces, gives me a net ocean current that is directed from south to north. Now we are 90 degrees to the right of the surface wind. So this process continues with increasing depth as you keep going lower and lower and lower within the ocean to about 400 meters, roughly 1,300 feet or so below the ocean surface, where there's been so much frictional dissipation that there's really no net ocean current left, at least not one that is associated with the surface wind. So here, if we come to this diagram at left, we can start with this surface wind here that is depicted by the white arrow. So we can assume that to the west is into this figure, and to the east is out of this figure towards us. So this first yellow vector here is 45 degrees to the right of that. That's giving us the ocean current right at the surface. This ocean current then induces a flow just below it, and that gives us this yellow vector here that is 90 degrees to the right of the surface wind. Then that one induces a current just below it that is deflected to the right by Coriolis. So we get this vector that is 135 degrees to the right of the surface wind. And then so on down here to 180, 225, 270, all the way around. We get this spiral that is clockwise with increasing depth in the northern hemisphere. And if we looked at it in the southern hemisphere, it would be counterclockwise with increasing depth. This spiral that we see here is known as the Ekman spiral. When we consider this entire depth that we have here, from the surface down to about 400 meters deep, Integrating or averaging all of these different vectors that we have depicted here associated with the Ekman spiral gives us an average transport 90 degrees to the right of the surface wind in the northern hemisphere, and it would be 90 degrees to the left of the surface wind within the southern hemisphere. So if we have an easterly ocean current, or an easterly trade wind, in the equatorial regions, whether we're in the Pacific Ocean or some other ocean, so that easterly current is directed this way. Ekman Transport says that the flow will be 90 degrees to the right of that in the northern hemisphere and 90 degrees to the south of that in the southern hemisphere. In other words, away from the equator. So reiterating that net upper ocean Ekman transport is away from the equator in both hemispheres for easterly trade winds. And so consequently, we get sea surface temperature distributions that look a lot like the one that we have depicted here, where we have South America here at right, we have the international dateline here at the far left, and the equator is this line here with my laser pointer tracing across the screen. Note that it is relatively warm just to the north of the equator, in both to the east and to the west, and really warm below the equator to the south, especially in the western portion of the Pacific Ocean. But right along the equator, it is relatively cool compared to areas to the north and to the south, especially in the central and western portion of the ocean basins. So that net upper ocean Ekman transport that is away from the equator in both hemispheres, as that water is carried to the north and to the south, or poleward, it is replaced by water from beneath, upwelling, that brings colder subsurface water up toward the surface. This effect is strongest here in the eastern portion of the basin, associated with the relatively strong trade winds that are found there, and somewhat less as you get further to the west in the basin, as the trade winds weaken somewhat, and you get the piling up of water driven by the surface wind in the western portion of the ocean. So that's all fine and good, but what about variability in that structure? If we think about this in a climatological mean sense, we'd always expect it to be relatively warm in the western portion of the basin and relatively cool in the eastern portion of the basin, whether that be the Pacific Ocean or otherwise. The most common or the most predominant form of variability in that basic structure is associated with the El Niño Southern Oscillation, or ENSO, which is a 2 to 5 year variation between relatively warm conditions in the east and central Pacific associated with El Niño and relatively cold conditions in the eastern and central Pacific associated with La Niña. And we'll talk a lot more about El Niño and La Niña in our next video, next couple of videos for that matter. But here as a very brief introduction, we'll describe how this varies between El Niño and La Niña. So during El Niño events, equatorial wave forcing, we'll talk about what that looks like as we get into our ENSO lecture materials. This equatorial wave forcing causes the climatological easterly trade winds to either weaken, become weaker easterlies, or even reverse, turn around and become westerlies along the equator in the Pacific Ocean. So since we said that easterlies are associated with Ekman transport away from the equator, which causes upwelling of colder subsurface water to the equatorial region, if we weaken those easterlies or even turn them around to westerlies, if we weaken them, that transport away from the equator becomes somewhat weaker. If we turn them around the other way, like so, that transport actually becomes toward the equator, which would cause downwelling of relatively warm water. So when the easterly trade winds reverse or weaken, that natural upwelling that takes place in the eastern and central equatorial Pacific Ocean weakens or changes altogether, which then causes it to be relatively warm in the eastern and central equatorial Pacific, and that forces ascent and rainfall to be found more so in the central and eastern equatorial Pacific as compared to normal. Whereas with La Niña, the opposite is true. Those climatological easterly trade winds actually become even stronger. So as you have even stronger easterly trade winds, that transport away from the equator due to Ekman forcing becomes even stronger. So that's going to force colder water up more readily from the subsurface to the surface along the equator. And this helps to accentuate or strengthen what is typically there. So the Walker circulation doesn't necessarily change where it is centered or located during La Nina, unlike during El Nino, but it typically becomes quite a bit stronger during La Nina than it is in the climatological mean. So this structure, this coupled ocean and atmosphere system characterized by the El Nino Southern Oscillation varies or oscillates with a period of about 2 to 5 years, usually about a year associated with El Nino conditions, then a transition to La Nina conditions, which may last from 1 to 3 years, and then a transition back toward El Nino conditions, albeit with a lot of variability in that general evolution. Shorter term Walker circulation variability, so focusing on the 1 to 2 month period, is driven primarily by the Madden-Julian oscillation, which we'll consider in a lecture series after we consider the El Nino Southern Oscillation. But very briefly as an introduction to that, there's some forcing, which we don't really have a good handle of even to this day, what actually forces or drives the Madden-Julian oscillation. But this forcing leads to an oscillation that has a repetition or periodicity of about 1 to 2 months, and it's manifest in our equatorial zonal winds and rainfall. So this changes where ascent is maximized in association with the Walker circulation, especially within the Indian and the Pacific Oceans, but to lesser extent within the Atlantic Ocean, if the Madden-Julian oscillation pulse is able to progress that far to the east from where it typically originates on the edge of the Indian and the Pacific Oceans. So now I want to close out this lecture video with a consideration of the Walker circulation structure. And we're going to focus very near to the surface in the lower troposphere here. And we're going to focus on 3 core elements. This first one is going to give us the horizontal velocity as well as the vertical velocity, resulting from patterns of low-level convergence and divergence. In the next one, we'll take a look at the pressure anomalies near the surface associated with this structure. And then in the third one, we will integrate this solution to show how it provides the full Walker circulation as we typically see it. So here we're using a simplified equation set, our shallow water equation set that we have described several times prior in this class or this course so far. Here, rather than just having the equations with no forcing, we apply a prescribed warming to ignite pressure and wind anomalies associated with that or driven by that warming. And so that warming is depicted here in the red bubble. It's centered here at 0 and 0, where y equals 0 can be taken to be the equator, and x equals 0 can be taken to be some longitude, arbitrarily chosen in this particular case. So this warming is relatively large in extent, and what we're looking at here is the velocity response, the horizontal velocity given by the vectors, and the vertical velocity given by the contours. So focusing on the horizontal wind, the vectors here for a moment, we see 2 equatorial wave types here. We see this easterly form of a Kelvin wave and this westerly form of a Kelvin wave here along the equator. And we see this particularly noticeably here to the east, and we can tell that it's a Kelvin wave because it has that characteristic structure with no meridional flow associated with this portion of the solution. Whereas to the west, it's not quite as clear because of the other feature that we see here. We have twin cyclones, one in the northern hemisphere and one in the southern hemisphere, associated with the cyclonic half wavelength of our n=1 equatorial Rossby wave. So this cyclonic half wavelength of the equatorial Rossby wave superimposes upon the westerly portion of the Kelvin wave to give us the structure that we see to the west, whereas it has less of an influence to the east, such that the solution there is dominated by the easterly portion of a Kelvin wave. We have ascent that is maximized where the prescribed warming is actually applied, and this happens to also be where low-level convergence. Note these easterly winds coming here toward the heat source from east to west, and these westerly winds coming from west to east toward that warming source. So those winds converge near the surface, forcing ascent through that heating source, a thermally direct response. We get weak descent given by the dashed contours here, primarily on the western fringes of the cyclonic rotation anomalies associated with the equatorial Rossby wave. Now if we take a look at the pressure perturbations, we've also got the horizontal wind vectors here to help with continuity from the previous image here. I've also depicted the prescribed warming location once again here with the red bubble. So this prescribed warming leads to reduced pressure everywhere across this analysis domain. These contours that you see here are all associated with negative pressure anomalies, reduced surface pressure in association with this prescribed warming. These pressure anomalies are maximized here with the cyclonic rotation anomalies associated with the n=1 equatorial Rossby waves, cyclonic half wavelength that we see here. But it is still negative everywhere, with this rocket ship turned on its side-like appearance here. So our reduced pressure extends pretty far to the east along the equator, and this is associated with that Kelvin wave's easterly half wavelength, which we know is associated with relatively low pressure from our stick in the wind type of arguments. We'd get clockwise or anticyclonic rotation to the north, counterclockwise or anticyclonic to the south, and so we infer relatively low pressures along the equator associated with this feature. Whereas to the west here, the westerly portion of the Kelvin wave we know to be associated with relatively high pressures. So we get kind of a counterbalancing situation here. Low pressure anomalies forced by this equatorial Rossby wave offset somewhat by the high pressure anomalies associated with the westerly portion of the Kelvin wave. The low pressure anomalies still win out, but note how these lower values of negative anomalies, so weaker pressure anomalies closer to zero, kind of nudge in from west to east along the equator here, offsetting those stronger negative anomalies to the north and to the south. So now if we take that structure that we saw on the previous slide, that lower tropospheric structure with the winds converging into the heat source and then ascending through the heat source, and we consider not just what we see at the equator, but over the entire range of latitudes that are considered here, and not just what we see at the surface, but the structure going upward too, all the way to the top of the model, which we take to be the top of the troposphere in this case, or the tropopause. We get this solution that we see here with the streamlines. So this is what we call the meridionally integrated stream function, and that's a meteorological jargon. Meridionally integrated just means that we're integrating or averaging over all of our latitudes that we depicted on our previous solution. And the stream function, specifically in the xz plane, just describes rotation within that plane, here in the x direction and in the z direction. So this is showing us how we have flow coming in from the west at low levels on the west side, and flow coming in from the east at low levels on the east side, converging here into the heat source, where the air then ascends over the depth of the troposphere, and then moves out to the east at upper levels on the east side, and out to the west at upper levels on the west side, with descent at larger radii, extending further and further away from the heat source, with greater extent to the east as compared to the west. So this structure, meridionally or latitudinally integrating what we saw on the previous couple of slides, is our solution for the Walker circulation, with easterly trade winds across much of the equatorial oceans, converging here in the western portion of the equatorial oceans, where we have our three different forms of diabatic warming, our surface sensible heating, our ocean sensible heating, and our atmospheric latent heating. We get ascent through those regions of heating, and then westerly flow aloft back toward the east across the equatorial ocean basins, with a relatively narrow region opposing that back to the west. We also see that our near surface pressure, so this trace here is the meridionally integrated pressure anomaly. So again, integrating or averaging over all of our latitudes that we saw on the previous slide. The negative anomaly is greatest just rearward of the heat source, which is where we found our cyclonic rotation anomalies with the n=1 equatorial Rossby wave. And it's negative everywhere. The zero axis is at the top of this panel here. but it's most negative closer to and just to the west of the heat source and becomes somewhat less negative as you go to the east and as you go to the west from there. So this simplified ocean-atmosphere coupled modeling system given by the shallow water equations allows us to elucidate how prescribed warming, whatever form or forms it actually takes, whether it's atmospheric sensible heating, ocean sensible heating, or atmospheric latent heating, whatever form it takes drives the zonal overturning circulation associated with the Walker circulation. Just as we demonstrated that it describes the meridional overturning circulation associated with the Hadley cell. And just as we can see from this, as well as from our previous materials, how such a heating can also drive the formation of equatorial waves. So from here, we're going to move into considering the predominant mode of variability associated with the Walker circulation, that being the El Niño Southern Oscillation. But this is it for our Walker circulation discussion.